depending on how you print your set of notes. I just want you to see that these are the terms ST, SL, diameter, and A1 as your area. So ST again, SL, and SB over there, and that's a diameter. If you print too small or kind of like too many slides into one page, then you wouldn't be able to see all this. So why do I highlight that? Because you would have your Lucid number expression, your Reynolds number expression that runs on your density multiplied by your velocity, the ambient velocity that's coming in. This velocity is written as Vmax multiplied by D, and why D? Because we are talking about those tubes, so it's not about length. Divide by your dynamic viscosity, mu. So this Vmax here, depending on your configuration, you have the aligned configuration or staggered configuration. The Vmax expression respectively will be given by these. And depending on, are you looking at aligned or staggered configuration? There are these two sets. I'm just going to put a bracket. Aligned, this one, a larger one. Okay. You have 4 sets of them, of which, depending on what's your Reynolds number, you would use the respective coefficient C1m, and this C1m would eventually make its way to this Lucid number expression over here. We have C1, and M that's over there. Okay? So again, I just want to repeat, consistent with the Glasgow message, this external flow over bank of tubes, they are not examinable, but you would need to know to understand your heat exchanger. Now I want to show you a video clip about this natural convection, and I'm going to fast forward that video clip so that we can save more time. What you can see over here is a heater. That's a heater that I was saying, if you were to go to Glasgow, maybe you can take a picture and send it to me. That heater is usually placed underneath the window. And you can see that part is dark blue. That's very cold air that's coming in because the ambient in Glasgow is colder. So that cold air is sort of like a sinking down, and this kind of like mixing together with the hot air due to the heater. So your heater will get heated up, and it will exchange its heat with a layer of air that's inside your room, and you can see that the hot air will start to become buoyant, and then it will circulate around the room. So I'm just going to fast forward that so that you can see eventually. This is done by simulation. It's not a photographic picture. So in simulation, we can see that how all this fluid starts to mix together. And eventually, you will see that the room will get more and more greenish in color, because the greenish color means that it's getting hotter and hotter, from green to yellow to red. And it ends up with more of your room getting warmer. So this is a good, nice way to heat up your room by placing the heater that's just right underneath the cold window. Now you have heard about Reynolds number over a plate, and we were saying that if Reynolds number were to be at a certain critical number, or lower than a certain critical number, we say that flow is a laminar flow. And that number would be 5 times 10 to the power 5. That's updated in your latest example. If the Reynolds number were to be more than 5 times 10 to the power 5, that means the flow that's over the plate is known as turbulent flow. This laminar flow will use a different set of Nusselt number expression. This turbulent flow will use another set of Nusselt number expression. That is for forced convection. And now we're in the topic talking about natural convection. So for natural convection, we would know that the flow is going to go up in that way due to the fact that, let's say, in this case, your plate is hotter. So if the plate is hotter than the ambient, you would see that the air layer that's right next to the plate will get heated up, and then it will become buoyant, and then you will kind of like flow upward naturally. Right? And we have seen before that the velocity that's near to the plate will be zero, and in this case, the quiescent fluid, that means fluid that is stationary, not moving, we call that quiescent fluid. This fluid would have zero velocity as well because, again, this is a picture of natural convection. It's not forced convection. So out there in the quiescent fluid, there's no flow out there. Unlike what you have seen before for a forced convection, in the ambient region, there is flow. So in this case, there's no flow. So you have this part here that has a velocity that's zero, and that part there that has a velocity zero. And the profile of the velocity will look something like this. And because the velocity that's near to the plate is zero, that means that air molecule over there will inherit the temperature of the plate, and that's why we have that temperature here as a hotter temperature, and then you will get lower and lower into the ambient quiescent fluid. So since in Reynolds number we could use that 5 times 10 to the power 5 to help us to determine if we are in a laminar flow or in a turbulent flow, in natural convection, we also have such a parameter to help us to decide. And that parameter is called Grashof number. Right? Grashof number. So Grashof number, depending on what you set number, it will help us to decide that natural convection. Is it laminar flow or is it turbulent flow? So that's the job of the Grashof number. I'm going to slide over to what you could see in your latest exam data booklet. Your Grashof number is written as this. So if you were to make a comparison between the two, you would see that that theta over here is actually represented as Ts minus T infinity. Now, you have to note this because it's not explicitly written as Ts minus T infinity. And it would also depend on which one is hotter. Is it Ts, the surface of the plate, or T infinity, your quiescent fluid? So if your quiescent fluid is hotter than the plate, that means you're going to use T infinity minus Ts. Okay. So generally we could put theta as that symbol over here to replace this part that you could see over here. So that one is written as theta in your exam data. There's also one other parameter that you have never seen before, that is beta. Now beta is defined as a volumetric thermal expansion, and actually beta is equal to 1 over Tf. So if you're wondering what is Tf, Tf is actually the film temperature. And in this case over here, this surface would have Ts, and Ts is greater than T infinity, where T infinity is a quiescent fluid temperature. So Tf is defined as Ts plus T infinity divided by 2. That is called your film temperature. Sort of like the average temperature between what is out there and the plate. So that will be your film temperature. If you take 1 divided by your film temperature, that will give you beta. Beta is a volumetric expansion, thermal expansion. There's one common mistake that students would make. This Tf here is in Kelvin, right? It's not degrees Celsius. I want to highlight that, right? please highlight that as well. 1 over Tf, where Tf is in Kelvin. If you put it in degrees Celsius, 1 over whatever degrees Celsius that you have is going to give you a different beta value. So a lot of students make mistakes in that, so please be careful of it. That's to say your beta would have the units of Kelvin to the power -1. Right? So if I just slide back again to look at the set of equations that so far have been discussed, again, this is your new set of a data sheet that you will use them to replace your first page in the set of data sheet that you already followed. If I just go over to this internal flow, taking some of this Nusselt number expression, for example, in the turbulent flow, you would see that your Nusselt number is a function of Reynolds number and Prandtl number. It's always the case for your internal flow. Forced convection, that's the case. If you look at some others, let's see if I can find another one. Your developing flow with constant surface temperature is also, Nusselt number is also a function of Reynolds number and Prandtl number. Right, that means it's dependent on these two dimensionless numbers, Reynolds number and Prandtl number. But if you look at your natural convection, all right, that was forced convection that I was talking about. If you now look at natural convection, you will see that your Nusselt number is actually a function of Grashof number and Prandtl number. So the expression that you can find would be something that looks like that. Free convection of a vertical plate, and I want to underline the vertical plate because this is only for the vertical plate expression. The Nusselt number is given by that. And this expression is also included in your exam data sheet. Let me just bring you to there. It's written over here. All right? So this is in your exam data sheet, the new one. You would see that in your set of notes, this power 8 over 27 is missing. So please fill that in. I've already highlighted this to Glasgow, and they say that indeed this one is missing. There's also another thing that I want to mention. Now this is an expression of Nusselt number for free convection and for a vertical plate. And in order to decide are we going to use this expression or not, there's this new term that you could see, there's RA, that is Rayleigh number. Another dimensionless number, Rayleigh number. Rayleigh number is Grashof number multiplied by Prandtl number. Okay? You would have already seen what is the respective Grashof number and Prandtl number. If I move over here, your Grashof number is given by this, your Prandtl number is given by that. That's in your exam data booklet. Right? So for the Nusselt number in natural convection, it is a function of both your Grashof number and Prandtl number. If you multiply these two together, then we call it Rayleigh number. Okay. If the Rayleigh number were to be approximately 10 to the power of 9, this is what we call the critical point that we use to decide are we in the laminar region or in the turbulent region for a natural convection. Okay? Not forced convection that we're talking about. For natural convection, it is lesser than, if the Rayleigh number were to be lesser than 1 times 10 to the power of 9, that means you're in the laminar region. If Rayleigh number were to be more than 1 times 10 to the power of 9, then it's in the turbulent region. So if RA X is less than 10 to the power of 9, this implies it is in laminar region. If RAX is greater than 10 to the power of 9, that means you are in the turbulent region. If Rayleigh number is exactly at 1 times 10 to the power of 9, we don't know, because in this case, it hasn't been defined yet. But in various textbooks, even this number itself will vary. All right, so it varies a little bit for different textbooks. In the case of Glasgow, they adopt that anything that's less than 1 times 10 to the power of 9, we call it laminar region. More than that, it's turbulent. And this is specifically for, again, free convection, for natural convection, and for a vertical plate. Other orientations, the textbook will give you a whole list of the Nusselt number expressions. So for now, this is the one that's only relevant in this module. Let's have a look at an example. This example has a glass panel, and this is actually a fireplace. So over here would be your chimney, and over here would be your living room. And there are a few parameters that are given to us. The surface temperature of that glass panel is 232 degrees Celsius. The quiescent air, that is your ambient air, that is not moving, that is at 23 degrees Celsius. This is the one that caught a lot of students unaware of. The height of that glass panel is 0.71. I'll be revisiting this again. And the width would be 1.02 meters. So I'm not sure, could you imagine? Height is this way, and width is going into the screen. That's the width. Right? Imagine that window is a rectangular window. So this window is partitioning between the fire place and the living room. Now there are a list of properties that we need to figure out in order to help us to find what are the physical properties of that we'll be using, things like your thermal conductivity, kinematic viscosity, diffusivity, Prandtl number. Your beta is actually 1 over your film temperature. In order to help us to determine all these properties, we need to express, we need to find out what is the temperature that we'll be using. In the case of, if you were to use Holman textbook, you'll be referring to table A5. And I think I have table A5 that I'll bring up. Is that this one? This A9? What is this one? A4. I have one that's A5. Okay. So I'll be using this later, but for now I want to elaborate more about this film temperature. Now the surface temperature of the window is at 232. Ambient is 23. So the film temperature will be calculated as your surface temperature plus ambient temperature divided by 2. It's sort of like the average temperature over here. That will be 232 plus 23 divided by 2. Calculate that, that's 127.5 degrees Celsius. And this is approximately 400 Kelvin. Why do I convert it to Kelvin? That's because in this table, A5, this column over here is telling me that this is in terms of Kelvin. Right. And very nicely, I have the 400 Kelvin that allows me to find out the corresponding properties over here. So these properties, as picked up from your Holman textbook, is actually different from what is written over here. That's because this one is adopting another textbook. So if you're asking, so if I were to do my tutorial questions, which will be coming soon, which one would I be using? We can use either one. Any of the textbooks property values, they will all work. Right? So in this case, I'm going to stick to this example over here, which is a little bit, those numbers are a little bit different from your Holman properties tables. Okay. So for Holman, if you refer, that will be table A5. The question asks us to find out what is the convection heat rate. Now this is a part that sometimes students find it hard to understand. The English word is convection heat rate. What is that symbol for convection heat rate? That symbol is actually just that Q symbol you've seen before. So it's asking you to find that out. This Q symbol is expressed differently using different English language. Rate of heat transfer, convection heat transfer rate. Right? It's a different way of saying the same thing. So let's go ahead and solve it. We know that for convection, and why I know that I'll be looking at convection, that's because this glass is heated up and you have no forced convection over there, so it is actually a natural convection that's going on in that way. This is natural convection. And the expression for natural convection will be HA delta T, in this case would be Ts minus T infinity, because Ts is at a higher temperature than your T infinity. And this H over here is also different. This is actually your average H. And H is your convection heat transfer coefficient, sometimes also called convective heat transfer coefficient, sometimes also called heat transfer coefficient. They all mean the same thing. But it has a bar over there, so you have one more word, average heat transfer coefficient. So in order to find out what is Q, we need to know what is H bar, and our job here is to find out what is H bar. Knowing that this is a natural convection, we have to first find out what is your Rayleigh number. Rayleigh number equal to G beta and the temperature difference Ts minus T infinity, and the length Q divided by alpha multiplied by nu, which is your kinematic viscosity. So G over here refers to your gravitational pull, so that's 9.81. In the exam, these numbers will not be given. Gravitational pull, of course, everyone knows that is 9.81, right? Yeah, now you know. And beta, we have kind of like solve it over here. That's 1 over your film temperature. So I'm going to copy it down, 0.0025. And the temperature, 232 minus 23. And the length over here, 0.71 cube, divided by alpha, which is picked up from your property table. That's 38.3 times 10 to the power minus 6. Multiplied by your kinematic viscosity is also picked up from your property table, 26.4 times 10 to the power minus 6. Now note, this is also another common mistake. This one over here, this guy over here, length. So if you look back at what I was saying, the height and the width. Let me zoom it in. Alright, this part here, the height and the width. Obviously, this is the height, and the width, if I were to kind of like sketch it, will be that way. So some students ask, why is it that this part over here, in your formula sheet, is written as x cubed here? Let's bring us over. In your formula sheet, it's written as x cubed. Over here, for your Grashof number, this is x cubed. Well, in your data booklet, there isn't Rayleigh number, because Rayleigh number is equal to Grashof number multiplied by Prandtl number. So if you take this, multiplied by this, you get your Rayleigh number. that is over here. That will be your Rayleigh number expression. So the thing is that some students are wondering, why is it that I take 0.71 instead of this width that's 1.02 over here? Now, if you look at how natural convection works, that natural convection is going to be buoyant, it's going to move upward. So that place where it's moving upward along that dimension, that is your dimension to use for this x cubed over here. Okay? So if the buoyancy had not been that way, for some reason there's a forced convection that's forcing it going this way, then the distance that you're going to get, you're going to use would be this 1.02 meters. But because it's a natural convection, it's not a forced convection, it's going up in that way, so we're using that height dimension. Okay, so the height dimension in this case is given as L, that is 0.71, and that's the one that they're going to be using. So if I were to solve this, I get 1.813 times 10 to the power 9, and just now we were saying the critical Rayleigh number is 1 times 10 to the power 9. In this case, is this larger or smaller than 1 times 10 to the power 9? It's larger than 1 times 10 to the power 9. It implies it's turbulent. And if it's turbulent, then we'll use the turbulent equation. That is your Nusselt number, average Nusselt number, is equal to 0.825 plus 0.387 Rayleigh number, 1/6 of that, divided by 1 plus 0.492, divided by Prandtl number, and this thing bracket to the power of 9/16, and the whole thing to the power of 827. And don't miss out that square over there. Okay. This equation will be provided in your exam data sheet. So now let's put in all those Rayleigh number and Prandtl numbers. That will be Rayleigh number, we have solved that, that's 1.813, 1/6. And Prandtl number, we had it right up here. Yeah, Prandtl number is right up here. 0.69, power of 9/16, 827. And don't forget, there's a square there. Now, I have said before, while marking exam questions, some students kind of like wrote everything perfectly, but calculated wrongly. What a waste. Don't let that happen to you. What you could do is practice, you know. It's kind of like, you know, I don't know, warm up your hands or whatever. Make sure you press your calculator correctly. You can only save yourself. So, if you make a mistake there, you'll lose some marks, okay? Do that calculation, that will be 147. So we know that the Nusselt number is equal to h bar L over K. And we were saying that our job is to find out what is h bar. So h bar, by re-expressing this whole thing, would be Nusselt number multiplied by thermal conductivity over your length. So we have found out what is a Nusselt number already, 147. The thermal conductivity from the property table, that was 33.8 times 10 to the power minus 3. Divide by the length. This length again refers to where your natural convection is happening across it. So that will be the length L. That's 0.71. Do the calculation, you should get 7 watts per meters square Kelvin. So that's not all done yet. Our job is to find out what is your heat transfer rate, of which the question called it as convection heat rate. So that is equal to H bar multiplied by the area multiplied by that temperature difference between the glass and the ambient. Put 7 into this. The area would be the area of the area of the glass. That was 1.02 times 0.71, and the temperature difference. Do that calculation, 1060 watts. That's your final answer. That sort of wrap up your topic about convection, and today we're going to move on to heat exchanger. Now, heat exchanger is a very important concept. In fact, next week when we start our lab experiments, you'll be dealing with heat exchanger.